Welcome back. So now we'd like to look at NMOS in the depletion regime. Okay. And we have seen in the last week that NMOS in depletion will have bands which are bent downwards. So for example, if I take this to be my equilibrium Fermi energy, EF, right? I'm depleting the MOSFET, P-type semiconductor. So I'm going to have bands which are bending downwards like this. Right? So now even EI will bend in the similar fashion. What will happen to the bands in the oxide and metal? Okay. So to analyze that, we have to think about what kind of voltage do we have to apply to cause depletion. So P-type semiconductor, this is P-type. So it has holes and you want to deplete the holes. So you want to push the holes away. So you have to apply a positive voltage. And when we apply a positive voltage, the metal Fermi level shifts down relative to the bulk. This is my VG, right? I'm applying a positive voltage, so it is moving down. This is EF of metal, right? So essentially what we are having is we have pushed the holes away. So there is a negative charge in the semiconductor. So we can draw the block charge diagram by introducing, let's say here, a block charge like this. This is my, I could call it Xn, or this Xn I could call it, or I could call this as the width of the depletion region. So I'm pushing my holes away, so I'm creating a depletion region. That's a depletion approximation. We have seen this, right, already. So because it's acceptor ions which are pushed away, so this is basically exposed acceptor ions. And now what happens when you have these exposed acceptor ions in a capacitive kind of structure? There has to be an opposite charge in the other side. So if this was minus Q, there should be a plus Q. And where will that plus Q be? As in the previous case, it has to be right at the interface. Okay, this is your balancing charge. So this is going to be plus Q. So if you have a plus Q and minus Q in this fashion, in the block charge, what will be the direction of the field? The direction of the field has to be in the positive direction. So I'll just mark it here. So I'll say that this is my direction of the electric field. It should increase in the, it should point in the positive X direction. Okay. So please remember that this is at interface, okay, because it's a metal. But now in the semiconductor, we have pushed away the majority carriers. So what we are left with the exposed acceptor ions. This is important. Okay. All right. So since we have a field which is positive X direction, how should the bands in the oxide be? Well, that is fairly simple. So what we have to do is there should be band bending in this sort of a fashion. So, okay, always remember this is a crude way of representing. Okay, it's not exact because this is, we know that this distance is 3.05 EV and this distance is 1.05. So it is only a schematic illustration. Okay, band diagram is not to the scale. Okay. Sometimes in some textbooks you will see that they'll put a small mark here like this. So that is indicating that it's extending, that there's a jump in the energy there. Similarly, there could be a jump in the energy. So that, we don't need to show it exactly to the scale. Okay. So, all right. So now, so this region here is basically negative charge. Acceptor ions. All right. So once we know this, what is the electric field? We have played this game before multiple times. So whenever you have a charge, E field is basically going to be dE by dx equal to rho. So in the semiconductor, I'll call it ESI is going to be what? I'll assume that the field is zero inside the bulk of the semiconductor. And as you approach the interface, there is a positive field, right? Because E is positive, because we have seen this. The direction is positive, so E has to be positive. So without actually solving it, I'll write it. And I hope that by now you're also able to write this. Okay. This is the electric field. So what is this ensuring? I know that because this is a uniform doping, right? Rho is uniform. Okay. Uniform accepted doping in semiconductor at least, right? So there should be a linear field, and the field has to go to zero at x equal to W, right? So that's why I'll draw my electric field in this fashion. Okay. So this is my Xn. Sorry, I should actually call it XP. Even in the previous case, I think I called it Xn, so let's call it XP because it's a P-type semiconductor. Please don't get confused. So make that correction in the previous video as well. Okay, I didn't mention this. Okay, fine. Yeah. So right now XP should be good. Okay. All right. Or if you don't want, oh yeah, sometimes we also call it as XD, X depletion. That's also another notation that we use. Okay. All right. So now what should happen to the electric field in the oxide? Okay. If I call this as electric field in the oxide, how much? Because there are no charges, right? No charges in the oxide, which we know that it should be constant. But what is that constant? That's what we need to determine, okay? So to determine this, we need to remember that we are talking of two different materials, right? So this is oxide. So epsilon of oxide is something, is there? No? Epsilon of oxide is going to be 3.9. Here it is silicon. Epsilon of silicon is going to be 11.7 or 11.9. I'm not very 11.7. I guess it should be. Okay. So please verify that number once. I'll do that in the next lecture. Okay. All right. So we have these two different dielectric materials. When you have electric field normal to the direction of the interface, then we know that d normal, d perpendicular, which is essentially equal to epsilon times E, right, is continuous. What does this tell us? It tells us that epsilon of oxide into electric field in oxide should be equal to epsilon of silicon into electric field of silicon at the interface. Right? This is essentially, this is at interface. Okay. So let's see what happens. Okay. So we have to find out what is the electric field, the constant electric field in the oxide. And okay, so I have a much better looking band diagram here. I'll just, for completeness, I'll just put this here, the same minus Q, and then there is a plus Q here. Okay, and we already seen that this should be a, let's say, XD, and this is your W. Okay. So now we saw that electric field in the oxide should be equal to electric field in silicon, silicon divided by silicon, right? So because of Gauss law, I mean, this is again coming from Gauss law itself, actually. Okay. So what does this tell us? It tells us that the oxide electric field, this is 11.7 divided by 3.9 into electric field in silicon. So electric field in silicon already I know, right? I mean, this will be Q and A divided by epsilon silicon times W. Okay. So this should be this is basically the, in effect, this is going to be 3 times epsilon electric field in silicon, approximately. Okay. So my electric field is going to show a jump here. Okay. So this is simply going to be Q and A divided by epsilon times width. This is going to be 3 times electric field, peak electric field in silicon, or rather you can call it this. Okay. So there is a jump in the electric field because it's two different dielectrics. Okay, so that jump has to be there. Okay, please remember that. All right. And then what is the electric field in the metal? Well, metal is zero. Right. So now how will the potential look like? Okay. To determine that, we'll just consider first, let's say, potential drop across silicon, or rather silicon depletion region actually, silicon depletion region. What is this equal to? We know the answer. We will just write it, right? I'll write it as V of x equal to Q and A by 2 epsilon silicon times W minus x whole square. Okay, you convince yourself. So this is for x 0 to xt. In the depletion region, this is going to be the form. Okay, you convince yourself that this is correct. Okay, if you are not comfortable, just make sure that you revise. Okay. So now the potential is going to be quadratically decreasing here. This is my V of x. And at x equal to xt, it becomes 0 and rest of it is all 0. Now what happens to the potential in the oxide? Well, it's a constant and that potential has to be continuous. So this is going to be a linear function. So whatever gate voltage we applied, now Vg, this is falling, part of it is Vox, which is linear across oxide. Okay. And this is Vx, which is quadratic. Okay, quadratic. So the total potential, the applied gate voltage potential now in the depletion is falling across the oxide plus actually the potential in the silicon. We will introduce a term which is called a surface potential in a moment. So this is surface potential. We'll define that. Okay, in a moment. So this is how the potential will drop, whatever applied gate voltage. So what is this? This is surface potential, and the way you define surface potential is this. Okay, let's say the same band diagram of a p-type semiconductor in depletion, and what you see is definition here, surface potential. It is defined as simply the EI in the bulk, okay, minus the EI in the surface. Okay, this is the definition of how to calculate, and I'll explain. It's a logical thing. In a moment, we'll explain how that is. Okay, so let's use what is the EF? EF was the phi f, not EF, phi f. This is phi f, which is simply the distance of the Fermi energy EF from EI, right? So this was KT by Q ln NA by NI. Right? This is what we know already. Okay. So now if you look at it, you can take EF and say use EF as a reference. Okay. So if you use EF as a reference, your psi s is going to be phi f in the bulk, right? This is bulk minus 0 at the interface. Okay. So this is going to be phi f in this case. Surface potential is phi f. Okay. So I mean, essentially, in a way, you can think of it like, you have this surface potential is this potential at this point, potential at the interface. Now you can call it is surface potential. Okay. So essentially, you have a positive surface potential, and then 0 in the bulk potential. So electric field is positive. So your bands are nicely bending upwards, which is consistent. Okay. And once you have this, your bands in the oxide are also going to be in the positive direction. Remember, always these are consistent, same direction, unless there is a interface charge, which is actually changing this. Okay. All right. So let's try to analyze, if you have this, we have seen the initial case, right, where at no applied gate voltage, wherein we had, uh, okay, and then, okay, there is a VG 0. So basically the bands were all flat. This is a condition, right? At VG equal to 0. So I'll call this as flat band condition. What is the surface potential at flat band? Psi S is equal to 0 at flat band. All right. Why it is 0? Because there's no band bending. So EI is same at the bulk and the surface, so it's 0. All right. So this is a useful term that we keep using. That's why I wanted to introduce this. And with that, I can also introduce the concept of inversion. Okay. So we will introduce inversion in the next video. So I'll meet you there. Thank you so much.